For those who don't know me, I'm Krishna Anisetti. I'm a technical architect here. Today we'll be looking at what's a big data. So firstly, thanks everybody for filling out the survey. We learned a lot of things, so we heard a lot of things from you guys, a lot of feedback, a lot of value from what you guys are looking for or you're looking to learn. Can anyone guess like how much percentage of people said they want to spend after hours for learning big data? Can anyone guess?
0.
It's 90. So that shows how much interested you guys are, how much passionate you guys are. So we want to provide you with all the resources. We wanted to empower you with everything what you need in order for you to learn, understand, and do stuff by yourself or with our help. So today we will be looking at what is big data and why we need to basically do big data. And Brian will be covering the basic concepts of Hadoop, and I'll be coming back and going over the various components of Hadoop ecosystem. I'll be just taking a sneak preview of each of the component, so you know what it is, so you can go back and learn more. And Jason will be going over what is big data at CARS, what it means at CARS, and what we have been doing in this space, and what we are planning to do. And we also give you the next steps, how you can learn using some of the planned workshops, learning material, and etc. And if you guys can stay back after 5, we can actually try some Hadoop using HIVE and stuff. Okay. So what is big data? Let's answer this question first. So there's a lot of definitions, definitions for this. So something which I like is it's a collection of complex and large data sets. Most of these data sets are usually used for doing complex analysis across. So before we understand what is complex and what is large data sets, let's actually look at few use cases. So big data is not something which only corporates are using. It's something which is improving our lives every day. It's impacting our lives every day. For instance, like last month, I got a text from Comet, my electric provider, saying that I'm overusing power compared to my my neighbors. So I logged in and looked at it. If you look at the January, so I'm like doing way high compared to my efficient neighbors. I'm like, all this is possible because as of last summer, Comet installed their electric meters, which collect data every hour, and they keep reporting back. So they're collecting data every hourly from every household. Look at how much of volume it is. So all of this is possible because they were able to find out that averages with my neighbors and find out what is going on and alert me at the real time. By the way, it was my thermostat which was not working, which caused it. So the other thing is the fitness trackers. So most of us are using fitness trackers. There are 100K fitness apps available in both app stores, Android and iOS and Windows. So each of these fitness tracker, think about how much of data they are collecting. They're collecting a lot of data. They're collecting the number of steps, your sleep time, heart rate, and many more. So think of how much data each individual is producing and how many millions of people are producing. So all of this data is in turn helping us. It's giving us suggestion on how we can improve our health. When we need to walk, that we need to work out, we need to do. So it's giving back us all this information. It's making us more better and healthy. So the other one is the Uber. So all of you guys would have seen the screen, the search pricing of Uber. Think of how Uber calculates this. So Uber looks at the current demand and the demand or the historical demand for that area, and it actually calculates the search pricing. The search pricing is not just to make us pay more, but it's also to attract the drivers on the places where there is no demand into the areas where there is more demand. That way they can meet the demand of what they have. So so Uber is able to do this at real time, looking at a lot of data, and again because of big data. So we have looked at a lot. So some are real time, some are batch. Some analysis are happening in the background, some are happening at the real time, and many things. So let's actually brief what are the characteristics of big data. There are 4 primary characteristics of big data. So volume, variety, velocity, and veracity. People also say value is another dimension, but I picked only 4. But again, these are something which I picked. So let's look at the volume. Can anyone guess how many bytes of data do we generate globally? At least how many zeros? No, it's 2.5 quintillion bytes of data. So that's per day. And 90% of this data was generated in the last 5 years. So the data is growing exponentially. It's growing, I would say, at a 50% rate of what is available. So it's growing really exponentially. By 2020, people are saying it will be 40 zettabytes, and there are like out of the 7 billion population, 6 billion people have cell phones. So look at how much of data
each
mobile phone is emitting. So there's a lot of data. So we need to have cheaper hardware. We need to have cheaper hardware to store the data. We no longer can make it an expensive thing, and we need to capture every detail to find out some interesting things. So we looked at the volume. Let's look at the variety. So when we speak of, so traditionally we have been doing a lot of relational data. So which it means is that the data has some attributes or properties to it. But think of a video. Why can't it be a data? It is something which a human is expressing about what it is. So there's something we can find out looking at the video, as an image, as a tweet. So there are a lot of types of data which does not have a structure. And we don't want to actually extract few attributes of the data and store just a structure. What if tomorrow we find out that that particular video has some hidden thing which we wanted to dig? Once we lose the data, we lost it. So we need to store the data in the raw format. And there are like lots of billions of Facebook comments or posts and a lot of videos and everything. So the nature of the data has changed from relational to from structured to unstructured. So there is a lot of need for it. Big data is something. One of the goals for big data is to how can we technologically solve and find out meaningful information from this unstructured data. So the other one is the velocity. So think of how many text messages are going from WhatsApp in a minute, in a given minute. Think of like how many messages are going from Verizon or AT&T or any provider, number of text messages going out through Verizon. So it's the volume at which the data needs to be processed. It's not just that the message is going through, but you need to process, like a WhatsApp message, it needs to be processed and put it to the receiver. You need to know where this has to go. So this is something it has to be processed. So it's the rate at which you are processing the data, at which you are receiving the data and also processing. So there, like if you look at the New York Stock Exchange, 1 terabyte of trade information is what it is for every trading session. So every day there's a 1 terabyte of data coming, and they need to process in minutes, in seconds, in order to do the trading. So there's the velocity of data has really gone really fast. The next one is the veracity. So it's about the confidence of data. So 1 in 3 business leaders said that they don't trust the data they are actually they're being presented with. So they don't have confidence on the data insights what it is. So it's more about like we need to solve the problem in such a way that we build confidence. We need to give more and more granular details which make them confident. Sometimes they hear like, we don't know how this was derived, but this is what it is. This is the factor. But we need to give all deeper dive of like how this is derived, which will make a leader or anyone to be confident about that. That's another key goal of like to solve for big data. So these are the 4 problems like big data brings, and some technology which needs to solve. So Brian will be going over Hadoop, which is one of the framework which solves some of the problems of big data.
So what I'm going to cover is a little bit different. Basically, what we're going to cover is why Hadoop really emerged the way it did. In a lot of ways, Hadoop is the convergence of a lot of different technical concepts that occur both in the file-based world as well as the database world. And so we're going to cover kind of why and which of those concepts really led to the emergence of the need for a unified framework that could bring a lot of these things together to solve the problems that Krishna was just discussing. So basically, from a historical perspective, we're going to start with sort of why and how Hadoop evolved. Then we're going to talk a little bit about what differentiates Hadoop from a traditional RDBMS, and basically when you would use Hadoop versus a traditional RDBMS, and also specifically when not to use Hadoop. Because effectively, a lot of times people are like, big data, well, it's high volume, therefore we use it for everything. It doesn't really work that way, so we'll cover some of those details. One of the major concepts that's also involved with the emergence of Hadoop and how to optimize Hadoop effectively relates to a concept called MPP, or massively parallel processing. So a lot of people that come from the Teradata world should be very familiar with a lot of those concepts. Not to tee it up or anything. And basically the other piece I want to cover is the fact that everybody kind of knows that big data is involved with volume and high volumes of data. But it's actually a lot more than that. It's more about the iterations that you might be going through a data set looking for very specific things. And finally, I'm going to kind of discuss the emergence of new concepts within the Hadoop framework, how it emerged, and then we'll transition to the actual components themselves, which Krishna will then cover. So basically, Hadoop started, and you can kind of go all the way back to the early 2000s. And like most technologies, it started out with a white paper that came from Google in 2003 that basically explored the idea of using a file system to do data processing, which was a relatively new concept at the time. Most of the time, like when we think about databases, databases emerged because you needed someplace to store and analyze data. File systems emerged because you needed someplace to store data. But the idea of converging those was a relatively new concept at the time as technology was emerging. So something called Nutch was sort of the initial basis that led to the framework of Hadoop. But strangely enough, and this is one that I find relatively surprising, the very first instance and deployment of Hadoop didn't actually come until a few years later in 2006. A guy by the name of Doug Cutting, who currently works for Cloudera at the time, developed the very first distribution of Hadoop for the HDFS file system itself. Does anybody know what Hadoop stands for or where the name came from?
Yep. Elephant.
Yes. So Doug had a son at the time. I don't remember how old he was, but basically his son had a toy elephant, and he was trying to figure out what to call this system that he developed. And so it was effectively called Hadoop, named after that particular elephant. That's why you see the elephant in all the iconography and in all the different names derive off of animal and elephant-related names, which is kind of interesting. So in 2007, Yahoo basically took the initial white paper, or the initial white paper that Google wrote, as well as the distribution and technology that Doug Cutting wrote, and actually created the first 1,000-node cluster in HDFS itself. Now, originally, HDFS is written largely in Java, and most Hadoop frameworks are largely Java-based. Around the same time, after it went out to Apache, so first off in 2008, it was published as the very first 0.01 release as part of the Apache framework in 2008. So shortly after that, in 2009, basically a bunch of different people started looking at the Hadoop system itself and tried to figure out what they could do with it. So HDFS was originally written in Java. A company that actually emerged at this time, you might have heard of MapR. Raise your hand if you've heard of MapR, actually. People heard of it? Excellent. It's also one of the primary distributions that's currently used in EC2 today. But effectively, the big difference between MapR and the other commercial distributions of Hadoop, right around this time, it was 2009, 2010, is they decided to rewrite all of HDFS in C to basically allow for greater performance as well as direct NFS connectivity to get data in and out. So it was kind of a different concept, but that led to different companies starting to experiment with different ways in which they could use the Hadoop file system itself in order to accomplish specific tasks. And then basically as different use cases started to emerge, you might have heard of like in-memory databases, in-memory processing. Now, in the past 3 to 5 years or so, one of the big pushes is to actually incorporate real-time memory processing into the Hadoop framework itself. And that's actually where IMPALA, which you might have heard of, has derived from. And then finally, they wanted to take the Hadoop ecosystem, and it was very, very good for kind of single use cases, single pieces, but they wanted to expand it to be more of a framework that you could incorporate different components into. And the original framework was kind of cumbersome in the way in which it managed each of those components. So we'll also get into Hadoop 2.0 a little bit later in the presentation. So who are the major players in the Hadoop space? I mentioned Cloudera and MapR specifically. And basically, each of the major companies, so you've got IBMs, your Microsofts, there's a lot of different companies that are playing in the space. But what's interesting is that each company is kind of taking their own spin and their own approach as to how they actually want to offer their services. So EC2, as an example, when you get a Hadoop instance, they're actually using the MapR distribution. It's actually now called Redshift. You might have heard it referred to as well. But it uses that engine for that. So what you started seeing is a series of alliances between the companies that make the distributions, so your Hortonworks, your Cloudera, your MapRs of the world, and then they started creating alliances with the bigger companies that were offering a lot of cloud-based offerings. And so that's sort of how a lot of the actual companies started to emerge. So from a technical perspective, what is the difference between a Hadoop-based system that's performing data analysis and a traditional relational database? So who can tell me what unstructured data means? Any guesses? Okay, well, let's start more basic than that. Who can tell me what structured data is?
Tables, right? Tables, right?
Tables. That's a good place to start. Has anybody here ever heard of Kimball? Ralph Kimball. Who is Ralph Kimball?
Data warehousing guru.
And what was his big thing?
Normalizing data.
Yes. So effectively, highly transactionable data using fact tables. People might have heard of fact tables. Star schema. Excellent. So basically, these were data models that were basically used for a certain type of analysis. How about third normal form? Anybody? Ben, you're nodding. What's third normal form?
Well, there's different stages, right? So you go through first, second, and third. The first is like each column in the data has to have the same data point. And, like you can't have a column that one set is the size of your shoe, and the second row is the color of your shoe. You can't overload columns with data, and I can't remember the third.
You're generally, just from a conceptual perspective, you're generally using the tables and the structure to define what it is the system is processing, where you don't have to necessarily like go through, or you really have to go through and map out what that looks like ahead of time in the structures. So when we talk about structured data, we're typically talking about those types of tables, those types of structures. When we talk about unstructured data, what we're generally referring to, you might have heard of the concept of metadata. Everybody hear of metadata? So basically, if you have a file in your system today and you right-click on it and go to properties, one of the things that you'll notice is there's things like a creation time, who created it, what that person did. It might be a date modified, who has permissions to see it, those sorts of concepts. So at a file-based level, you have all this other data that's associated with that file itself. This is a very important concept to understand because now imagine, instead of having a file where you just have those fields to choose from, imagine something like an XML doc where you're actually defining what those attributes look like. This is a very important concept to Hadoop because basically that metadata is then what's used for analysis and processing. So basically, the other thing that basically allows for is the idea of analysis versus throughput. So who here has ever heard of OLTP?
Online transactional processing.
Yes, and what's that mean in more generic terms?
Transactional database.
Transactional database. So it's about recording what happened, about transactions that occur that are moving through the system. How about OLAP? Anybody OLAP? OLAP, Naveen. Analytical processing. So one of the things that Hadoop really endeavors to do, these used to be two very independent worlds where you had OLAP and multidimensional analysis, and then you had OLTP, which is more about getting data through the system to deliver it to a particular location in a particular format. Hadoop is an ecosystem that combines these ideas into a single environment in a single infrastructure. So what this basically comes at the cost of is what we generally refer to as concurrency. So if you have a traditional Oracle database, you can have lots of different people that are querying that database at the same time. Hadoop ecosystems are generally optimized for throughput. You want to get people in and out as fast as you possibly can. So in terms of when you wouldn't want to use Hadoop, You wouldn't want to directly query Hadoop if you're actually trying to serve content onto a website or something of that nature. You would want an intermediary. So who can tell me a little about MPP? What does MPP mean? Massively parallel processing. I wonder where you got that from. But what does that generally mean from a processing perspective? Like, how is that different from your Oracle database that sits on a server somewhere? So the way I like to describe it is if you had a deck of cards, right, and you were trying to optimize how do you discover how many jacks are in that deck of cards, you would traditionally add a lot of indexing. You would order the cards in a specific way so that when you get to the jacks, you can see, okay, there's 4 jacks. In an MPP world, what you're doing is you're taking that same deck of cards and you're dealing them out to many different nodes, and you're asking how many nodes happen to have a jack. So it's a very different kind of conceptual processing. The way in which it's optimized is basically by something called sharding, where you're effectively distributing each of your data sets to many different nodes. So that way, a traditional explain plan, like in the Oracle world, would all be about how it's going to find it within that single node. In an MPP world, it's all about how you would actually find and then re-aggregate the data that you're asking for. So it's a little bit different, but from an optimization perspective, all of the components that are going to be talked about later are also distributed across these different nodes. So that effectively, if you're actually running a method or running a piece of code, you're actually running it across all of the nodes in parallel, not just on a single node. Does that make sense? Cool. So the other concept that's also important to note, we mentioned that big data is a lot more than just volume. So it's easy to say, like, you could just store terabytes, petabytes, exabytes of data in a Hadoop environment. But from an effective perspective, if you're querying that information, it's a lot of data to access at one time. So using the MPP concepts we mentioned before, one of the things that's a little counterintuitive, especially if you come from the data world, is that you actually prefer full table scans, full scans of your complete data set in the Hadoop world, and you want to iterate through that many times applying specific conditions. So you might be looking for something, whether it's a count, whether it's an aggregation, whether it's whatever you happen to be performing, you effectively want to distribute that across many different nodes and then scan your data through multiple times to then figure out what you're trying to find. So it's a little bit different than just the volume of data to do one pass. Like if you were to do a select star within a Hadoop-based system, it would actually return relatively quickly because of the parallel nature in which the data is surfaced. So as you're going through, it's easy or it's helpful to kind of think of it in terms of iterations. And then finally, in terms of the evolution of Hadoop, Hadoop really started out as more of a single usage kind of environment, mainly as it related to batch processing. In 2013, when the Hadoop 2.0 framework came out, the big difference is there's this new component called Yarn, which is a unified resource manager. So if you have different components that are going to be referred to later, they're now managed by this component called Yarn. And actually, in the future, with Hadoop 3.0, which some of the reference architecture just came out, there's going to be even more consolidation. So that way, some of the systems that used to be very fragmented are being incorporated into the overall framework more directly. So basically, just to sum up, actually, we'll just move on. Any questions about kind of that material? Because everything else is going to be really within the context of understanding this. So before we move on, any questions? Excellent. Krishna is going to talk a bit about the ecosystem.
Okay, so we looked at what Hadoop is at a very high level and its history, but now we are going to do a deeper dive into a lot of tools which Hadoop ecosystem has, tools and technologies. So it's very overwhelming right now, the market with number of tools. There are like hundreds of tools to do a lot of processing. It's primarily because of various skill sets. Like Hadoop was initially started off as a Java project. It was all Java. But not all, I would say, we can't expect everyone to do Java, especially the ones who are dealing with data. So there were a lot of alternatives, and the problems have also evolved and changed. So there are a lot of alternatives for every problem how we solve. So today let's look at like what are the key things which happen within the Hadoop. So in order for me to process the data, first I need to ingest the data, which is to bring the data into my system, into Hadoop, and then I need to store the data. And then once I have the data stored, then I would need to process and analyze and serve. So, basically, these are the three key steps what we need to do in order to basically get the processing running. So ingesting the data. Ingestion is about like bringing the data into Hadoop. So you can actually, I'll start off with HDFS. So HDFS is the core, so it is how you store the data. So let's first start understanding like what HDFS is and how it actually works. So HDFS is a file system, Hadoop file system. It sits on top of the native OS file system. It is meant to write once, so you can't do a lot of random writes. So you write once, you're done. It's a file system, so it's about writing once and no random writes are allowed. And it is primarily optimized for large streaming reads than doing a lot of random reads. So it's primarily like if you're looking for streaming like a data by data, a sequence of data, that is what it is optimized for. But if you're doing randomly, you want like 5 random rows or something, it is not optimized for that. So the primary thing is that Hadoop does redundant data for various reasons. So first, Hadoop, a big file is actually broken down into blocks. The block is like typically like around 100 MB, which is configurable. We can configure it. So every file, let's say you have a 250 MB file, it's broken down into 3, like 100, 150 MB of each block size. And then this each block is actually copied into 3 different nodes. Its default is 3, again we can configure it. The reason why they do is like the main objective of Hadoop is to bring processing and data together. So if you're processing the data which is in its own machine, it's faster. So if let's say you have the block 1 in 3 nodes, and when it has to process, we would actually ask the same node to process. So based on the task when it arrives, we'll pick which one is better and efficient. So every block, all the data is cloned 3 times across the cluster. So that's how the data is, and there is a metadata is managed in the name node. The name node knows which particular node has what data, and when it gets a processing need, it says I need to process this particular data. It actually distributes and it assigns the task to a particular node, which it is very close. So instead of doing remote data processing, it will be doing local data processing, which will be faster. So we understood like how the data is stored. Again, I will be doing a very sneak high-level preview, so you know what each of these are. The idea is like we'll have deeper dive sessions, or you guys can go back and learn whichever you like here. So the next main thing is like how do we get data into Hadoop? So we can either get it in the batch mode, like basically schedule it like every day, every hourly, or whatnot, or real time. When like for example ALS, when the events are happening, we want the data into HDFS, let's say. So it can be either batch or it can be real time. Let's look at the batch. So batch, there are a couple of options are using shell commands. So there is an FS shell, file system shell commands. You can use that to put data, get data. So these are some of the commands I put there. So basically you can log into something called edge node. We will go over what that is, and then you can start typing in these commands, which will allow you to put files or get files, or you can do almost Unix style commands with just a hyphen prefixed in most of the cases, and these are just sample commands. So you can use this to put files into it. The other way is to use scoop. Scoop is something which is designed to transfer data from RDBMS like Oracle or Teradata or things like that, and HDFS. So this does very efficiently because it uses MapReduce. It uses map only part of MapReduce. I'll go over what MapReduce is, but it internally uses the same core of Hadoop. It supports JDBC. So as long as a particular RDBMS has a JDBC or ODBC connection, it uses that internally and does that. It is optimized for parallel data transfer all the data is transferred. So when you're transferring terabytes of data, since it's in Hadoop world, everything is distributed, parallelly you'll be transferring a lot of data, and it will do fast data copies. And there are also a lot of other ways like Java APIs. There are Java APIs, which is not highly recommended because there are so many other tools you can use. And there are also like some of the vendors, like let's say Teradata, they give you adapter or a plugin to get the data, which usually is like based on Scoop. It's written on top of Scoop. So these are how we do in the batch, how do we get the data into Hadoop. The other thing is the real time. So in the real time, I choose like KAFKA and FLUME. So there are more and more options for every of this, but I choose my primary top, which we have used or which we are planning to use in the near future. So KAFKA and FLUME are two best choices. KAFKA is a distributed queuing system, much like ActiveMQ or whatnot. It's that. The main difference is it's distributed. It's primarily a pub-sub model. Someone publishes the producers consume it and the consumers consuming. It's that, but it is primarily designed to be fast, scalable, and durable. So the topics are partitioned and replicated. So even the topics like where we are actually putting the data is replicated. We kind of like can have 3 replicas. So when somebody posts a message to the queue, it is replicated into 3 nodes. So you have 3 copies of it. And KAFKA does not actually attempt to track what are the messages which the receiver has already read. It does not attempt to do that. Instead, it will leave it to the consumer who is consuming the data to track what is happening. Again, just for scalability and the fast performance, it does not know what it is. So it just sets the amount of time. So you can configure to say like half an hour of data, keep in KAFKA and then expire. That's the only information it stores. It's all up to the consumers to track what is the amount of data they have already read and what needs to be read, so on. So the FLUME is another way, other system like where it is efficiently collecting and aggregating and moving large amount of data. So it's usually a client. It's much like a Dynatrace client or an agent, Dynatrace agent or any agent which will be sitting on the JVM or which will be sitting on the app server or web server, and it will be constantly pushing data to HDFS. And the beauty of FLUME is we can also do. It also has a lot of. It is built on top of reliability, so it has a lot of failover mechanisms. So it keeps backing up into the sink every often so that you don't miss any data. So you can configure this on a app server or web server, and it keeps constantly pushing the data to HDFS. So we look at a couple of real-time, the KAFKA and FLUME. Now let's look at processing or analyzing and serving the data. So typically, even before that, let's look at the YARN. Like as Brian was mentioning, this is something which is new, which came as part of Hadoop 2.0. So YARN is it is a resource management framework which is responsible to distribute the jobs. Like we were seeing before, like when I get a job, it's the responsibility of YARN to tell this node is fairly simpler, so it can go into. It's a centralized place where it does. Typically, YARN's infrastructure has these 3. It has a resource manager, node manager, and an application manager, which basically tracks what's going on and which has the data, and it keeps distributing it. So most of the frameworks which we will be speaking to process the data is using YARN in between. So now looking at the processing or analyzing or serving the data. So we can process the data in batch, like what we do with the ETLs today. We analyze the data in the batch. We can also do have SQL queries, SQL queries to do that, or we can do NoSQL. We can start storing documents on this, or we can stream live data and process the data while it is streaming. So the batch is something which has started really first. That was the core of Hadoop. So with the batch, we have like MapReduce, Pig, Hive, and Spark. MapReduce has been the core for quite some time. So I'll spend a little bit more time on understanding MapReduce because that makes you appreciate the importance of Hadoop and how it actually solves. So MapReduce typically has three phases: a map, shuffle and sort, and reduce. Usually shuffle and sort is something which the Hadoop ecosystem, Hadoop internally takes care of it. We typically write code for mapper and reducer. So let me actually go over an example that might actually help better. So let's say we have a stream of data like coming, like lines of data coming. So at the end of it, what we need to do is a word count, a simple word count, and this is like the best hello world example for Hadoop. So you guys can easily find this everywhere for reference. So at the end of it, what we are looking for is we need to count of each word. How many word has come how many times. So the way Hadoop solves, or what the mapper does is, firstly, this is distributed. The map is a job which will run on everything. So firstly, when we got this data might have been split into chunks, into the blocks, and have been distributed across nodes. So maybe it is distributed by line into 2 lines, and it is distributed across. So when a first mapper picks up, what it does is like it just breaks the words. So it looks at the first line. All it does is like it is breaking the word and putting a count 1. Even though, like, if you look at here, the is repeated twice, but it doesn't care. It's just putting one more row into the and putting 1. So all it is doing is a small breaking the chunk. It's breaking this into this. So every node on its own goes and does this. So you have the first node doing this, second node doing this. Then there is this shuffle and sort. What shuffle and sort basically does is like it tries to basically aggregate the data. So basically, if you see here, what it does is like it will basically say, for this word, I found 1, 1, 1, or 1, all these things, how many ever it is finding. So it is not summing it because we didn't tell it to. All it is doing is aggregating. So the value it is just putting by a comma separated thing here. So this is what happens in the shuffle, and then it again breaks it into chunks and it gives to the reducer. So it need not be the same mapper working on it. So you have 3 chunks of data now with the problem to solve, like to aggregate the numbers. So each reducer gets a chunk of data. So once each reducer gets, what reducer does is to sum, to look for what is the data, like for example the. So it will sum all the ones into it. So one important thing in the shuffle and sort is it's actually getting for example the keyword the across from all the nodes. So it's not just from one node. It had 2 nodes. It combined everything into here. So it has aggregated and everything put into here. So when it comes to the reducer, we are making sure that that data is here, is there. So let me go a little bit back here. So basically, let's relook at what we have just did. So what happened is initially the input files came. The input files are split into chunks, into 3 mappers. I had my example for 2, but this says 3. So it goes into 3, and then each mapper reads the record and does some thing, and it actually puts into the shuffle and sort. And then shuffle and sorts aggregates the data and makes it chunks and distributes it to the reducer, and reducers basically output the files. So you will, at the end of the MapReduce job, you might be looking at 20 or 30 files depending upon the number of reducers you have. So each reducer will emit a file. So again, as you saw, both mapper and reducer both are distributed here. So there's a lot of distribution which happens and solves. Do you have any questions on the MapReduce? Anyone? So the next thing I want to look at is like, so when MapReduce is all Java, so it's all Java code you write. So when people started doing this, there are a lot of data scientists or data people working in the data area where they're very used to SQL or scripting, ETL, and things like that. They were not able to adopt MapReduce or Java, and it felt very complicated. We really don't need to write Java code for simple things. Then the first thing which came out was like HIVE and Pig both came. So HIVE was something which was developed by Facebook. So Facebook looked at this problem and said, like, why don't we actually abstract it as a SQL, but internally let it create MapReduce. So what it does is like you write as a SQL language, but it actually generates MapReduce jobs for you. So you write HiveQL, which is almost close to a SQL. With like as you see, this is an example over there. So it actually looks like SQL. So once you do that, Hadoop internally parses the SQL or HiveQL, and then it makes optimizations based on your query, and it will actually plan the execution, and it will generate the MapReduce jobs, and it will submit it. So at the end of the day, even though Hive is making life easier writing scripts, internally it is actually submitting MapReduce jobs here. So for Hive to do that, you need to have a table structure. So a table, you really don't need to have a table like RDBMS or anything. It's just a metadata. It's just like a metadata on top of a file. So you can just have files in a folder in HDFS, and you can tell that I need a table out of all these files in this folder, and you can basically tell the first field is this column, the second field is this column. So you would store in something called a meta store. There it will have mapping. So all the files are stored in HDFS, but the metadata is stored in in a RDBMS kind of a structure. structured in a meta store. So it have managed. So whenever you run the query, it will first get the metadata, then it looks at the files and get the data. So the next thing is the Pig with the similar problems for the ETL developers and for scripting people who are really into the scripting. So this was developed at Yahoo, I think Yahoo. So Yahoo looked at the problem in a different way, and they wanted the script. So, the main goal again here is flexibility and maintainability. This is how it looks like. It's more of a scripting language. You'll have a set of actions that needs to be performed in a particular data set. So it's a very high level language for expressing the data analysis. Again, Pig is also something which internally it generates MapReduce jobs, and it actually submits the cluster. So it pre-processes, parses the Pig, checks the data types, and does. One thing to make a note is like this does not require a table. Like Hive requires a table to be created on top of a file. This does not require to be do it. So it can be semi-structured data. It need not be structured data. So it can be semi-structured data, which it can do. And there are a lot of built-in functions Pig actually gives us. But we can always create a UDF or user-defined function in Pig, which we can do custom processing to. Okay, so all of this were running on MapReduce. As you see, Pig and Hive were on top of MapReduce. MapReduce is not something which is really fast. It's slow. So you will see, like especially when you are looking at small sets of data, it takes longer time than the relational databases. Like if you compare Teradata and Hadoop for let's say 100 MB of data, Teradata will win. But whereas if you compare for billions and billions of data, that's when Hadoop actually wins. But it's slow. People were like, so they don't want it so much of slowness in processing. They wanted speed. So Spark is something which has evolved with that problem in general to solve. So it's a generic compute engine which is on top of HDFS directly, and it's not on MapReduce. It bypasses MapReduce and uses its own processing framework. Some of the common use cases are iterative algorithms or doing some complex operations and machine learning. So Spark has APIs in Java, Scala, and Python, so you can write in your own thing, but internally it uses the Spark framework to do it. It's faster compared to the other ones. It's a totally different way of processing the data. So that's Spark. So the other thing is, like, even though Hive is SQL, but it is internally doing internally submitting MapReduce. So the other way to look at and process the data is to have just a SQL. So Cloudera has come out with this IMPALA, which Brian mentioned briefly. So IMPALA is a very high performance SQL engine for vast amounts of data. So it's similar to HiveQL. So it also uses the same meta store, which we looked at for the thing. It uses the same meta store, but it's faster. It's 10 to 50 times faster than Hive and Pig. Why is it faster? It's not on MapReduce, and it has its own implementation to look at the files and process the data. So that's IMPALA. So and then NoSQL. So basically, when we looked at HDFS, we said that it's write only. So we do a lot of writes and not optimized for read. But we know that always we need to write multiple times. It can't be write once. So that was one of the problem HBase was solving, and it's also a document store. It's a column-oriented database. It's a NoSQL database. So it uses internally the HDFS as the underlying storage, but it allows to do real-time read and write, random access on a huge data set because it stores by column and it stores as a document. That's the main reason why it does. So it's a NoSQL like Couchbase or something, but it has its own differentiators. But it primarily uses HDFS as its file system. The last one is streaming. So basically, the example of Comet, which I was saying, it was like it sent me a text message right and then, like when it was processing it. So you need some kind of alerts, like in banking industry or in many places, we need alerts at real time. So Spark streaming is something which does. So it is an extension of the core Spark API which we saw, but it processes the data in a stream. So it can process data from KAFKA or FLUME, which we looked at as the real-time ingestion, or even from HDFS and many other places. And it can actually write it. There are a lot of Spark plugins to write to HDFS or Couchbase or anything, any databases. So internally, if you look at it, what Spark Stream is doing is it's taking a stream of data and it's doing kind of a micro batch. It's chunking the data into batches of input data and passing to the same Spark engine which we saw and running it. So that's what the Spark streaming is primarily doing. It's just processing a batches of data. That way, since it's a micro batch, you get the feel of a real-time processing. So I want to go back. So these are all the tools I went through. I know there are a lot of tools and everything. I hope you guys got a sneak preview of what each of this is. So you know when you need to do a particular thing which you are interested in, you know which tool to look